Yeah, good evening and welcome to the another session of chemistry. In previous class, we are discussing chemical bonding, and particularly in chemical bonding, we have just started hybridization state. So I'm repeating again, hybrid state is one of the most conceptual part of complete chemistry, you can say. And with the help of hybridized state, you can find out the properties of given compound as well as including, the strength of the bond, geometry around the central atom and many more things. So in last class till now, we have seen the hybrid orbital can form sigma bond or it can accommodate lone pair of electron. Another thing we have seen in the case of, hybridization, it decides the geometry of the molecule. For example, if we have sp hybridization, geometry is going to be linear. If we have sp2, it is trigonal planar. If we have sp3, it is going to be hydral geometry. Now in these different geometries itself, here we are discussing some example in the last lecture also. The same sequence will continue the examples of hybrid state also. So till now, any hybrid orbital. So again, I'm repeating, the chapter is same as this chemical bonding. And it is chemical bonding, you can say session 3. Chemical bonding, and it is third session. It is hybridization. So till now in hybridization, we have seen it is intermixing of atomic orbital having nearly same energy. It is intermixing of atomic orbitals having nearly same energy. Any hybrid orbital can form sigma bond. Any hybrid orbital can form sigma bond, or it can accommodate lone pair of electron. Any hybrid orbital can form sigma bond, or it can accommodate lone pair of electron. Further, number of hybrid orbital required If we have 2 hybrid orbital required, it will be sp hybridization. 3 hybrid orbital, it is sp2. 4, it is sp3. If we have 5, it is sp3d. If we have 6, it is sp3d2. Here the geometry is going to be linear. Here geometry is going to be trigonal planar. And if we have one lone pair of electron, this geometry should be bent. Here the geometry is tetrahedral And again, depending on the lone pair of electron, the geometry may be bent or geometry may be, trigonal pyramidal. In sp3d, it is trigonal bipyramidal. So you can say it is TB. So it is trigonal bipyramidal geometry. And again, depending on the presence of lone pair of electron, it may be seesaw, T-shape, and linear. sp3d2, the geometry is going to be, octahedral geometry. So in sp, we have linear geometry. In sp2, it is trigonal planar. sp3 is going to be tetrahedral. sp3d is going to be trigonal bipyramidal. And sp3d2 is going to be octahedral geometry here. Now, again, if you see some questions based on this geometry and hybrid state is, that's the question is, find out, hybridization state of central atom in following compounds. Find out hybridization state of central atom in following compounds. Yeah, particularly you can say in following ions, and also predict their shape or geometry, let's say. And also predict their shape of the molecule. So as per ions are concerned, this may be, let's say, CH3 plus. It may be CH3 minus here. This may be, let's say, hydronium ion. This may be, let's say, NH4 plus. It is BH4 minus. The ions may be, let's say, ICl4 plus. It is ICl4 minus. This may be, let's say, ICl2 plus. It may be ICl2 minus. It may be, I3 plus. It may be I3 minus, and so on. So suppose it is, you have to find out hybridization state of central atom in following ions, in following compounds. So if you see, the first hint, first note related to this is, the note is, in all these ions, surrounding atom is hydrogen or, let's say, halogen. So if surrounding atom is monovalent, we have only one valency. If surrounding atom is monovalent, then if surrounding atom is monovalent, then charge of ion should be appeared, and the charge of ion should be appeared on central atom. Charge of ion should be appeared on central atom. For example, let's say first one, if we have CH3 plus, in the case of CH3 plus, carbon, if you see, initially its valence shell consists 4 electron in ground state without any charge. Here the positive charge should appear on the carbon. So positive charge means it has to lose 1 electron and only 3 electron remaining in the valence shell of carbon. Out of these 3 electron, it is forming, 3 sigma bond with 3 hydrogen. 3 hybrid orbitals will be required. 3 hybrid orbital means it will be sp2. In sp2, this geometry is going to be, trigonal planar geometry, in which central atom carbon is found to be sp2 hybridized, and it is forming 3 bonds with, hydrogens here. And overall, this carbon having positive charge. So it is CS3 plus, and it is, trigonal planar geometry. CS3 plus. So if surrounding atom is monovalent, then the charge of ion should be appeared on central atom. For example, in this case, if it is CS3 plus, carbon having, total 4 electron, the meaning of CS3 plus, carbon having positive charge means it can lose 1 electron, only 3 electron remaining here. Central atom carbon is found to be sp2 hybridized, and it is trigonal planar. Same, let's say if we have, let's say second as CS3 minus. In CS3 minus, out of 4 electron in total, it has additional 1 electron and total 5 electron now. Out of 5 electron, carbon forming 3 sigma bond with 3 hydrogen atoms, and thus overall it consists 3 sigma, and let's say it has 1 lone pair of electron now out of 5 electron. 1 lone pair and 3 sigma bond. 4 hybrid orbital will be required, and thus it is central atom carbon should be sp3 hybridized. Its geometry should be this carbon having lone pair of electron. This will be another hydrogen atom here, and let's say hydrogen atom, and this may be another hydrogen atom, and carbon should have negative charge. As per this geometry is concerned, it is trigonal pyramidal geometry. Trigonal pyramidal geometry. Same in the case of, let's say, H3O plus. In H3O plus, oxygen initially consists 6 electrons in its outermost shell, being positive charge on the oxygen. It can lose 1, only 5 electron remaining here, and out of 5 electron, it is forming 3 sigma bond and 1 lone pair. Overall, you can say it is sp3 hybridized. Here it is lone pair of electron on oxygen. It is, let's say, hydrogen. This may be another hydrogen atom here. And this may be, let's say, another hydrogen atom and oxygen having positive charge. So it is nothing but, let's say, hydronium ion. Again, this geometry is found to be, trigonal pyramidal. So it is also found to be trigonal pyramidal geometry, similar to geometry of NH3 ammonia. Next, if we have, let's say, ammonium ion NH4 plus, initially nitrogen consists 5 electron, but due to positive charge on the nitrogen, it can lose 1 electron, only 4 electron remaining here. Out of 4 electron remaining on nitrogen, it is forming all 4 sigma bonds here. So as we have 4 hydrogen, with every hydrogen, nitrogen will form 1 bond. So it consists, let's say, 4 sigma bond, no lone pair of electron. In this case, it is hydrogen, it is another bond with hydrogen. It is bond with hydrogen, and let's say another bond with hydrogen, and it is NH4 plus. This geometry is going to be, let's say, tetrahedral, NH4 plus, similar to geometry of CH4. Similarly, in same manner, if we have, let's say, BH4 minus, in BH4 minus, boron initially consists 3 electrons in its valence shell. Due to negative charge, total it has 4 electrons. And 4 electron we can have, let's say, 4 sigma bond, no lone pair of electron remaining, and thus this carbon or this boron is again found to be sp3 hybridized. sp3, you can represent this as, let's say, boron having negative charge, it is hydrogen bonded with hydrogen. This is another bond with hydrogen, and let's say bond with hydrogen going inside the surface of board. This geometry is found to be, tetrahedral. If we have ICl4 plus, iodine is halogen. Its valence shell consists 7 electrons, 7 minus 1 due to positive charge on the iodine. 6 electrons remaining here. 6 mein, out of 6 it is forming 4 sigma bond with 4 surrounding chlorine. And obviously it is form 1 bond, or it has 1 lone pair of electron also out of 6 electrons. As per its hybrid state is concerned, it will be sp3d hybridization. sp3d, 1 lone pair. That lone pair should always occupy equatorial position, and this geometry around central iodine atom should be. So this iodine consists lone pair of electron. This chlorine coming outward, and this chlorine going inside the surface of board. This may be chlorine atom, and iodine should have positive charge. So it is ICl4. This geometry is going to be, seesaw. So it is seesaw shape. In this case, it is ICl4 minus. In ICl4 minus, iodine consists 7 electron plus 1. Total it has 8 electron. Out of this 8 electron of iodine, it is forming 4 sigma bond, 2 lone pair of electron, and thus it will be, let's say, sp3d2. In the case of sp3d2, it is iodine and, let's say, chlorine going inside the surface, another chlorine coming outward. This is chlorine, and let's say this is another, chlorine atom. It is nothing but ICl4 minus, and in the case of ICl4 minus, it has, iodine carry lone pair of electron, and this iodine also carry lone pair of electron. Overall, it should have -1 charge on ICl4 minus. This geometry is, square planar. Square planar geometry. So I'm repeating again. If surrounding element is monovalent, including hydrogen or halogen, whatever charge we have present on ion, it should be appeared on central atom only. For example, in all these cases, whatever positive charge or negative charge present, it has to be present on the central iodine atom. Next is, let's say if we have ICl2 plus, or same, you can say this may be, let's say, I3 plus. The both is similar case. Iodine is central atom here, and out of 7 electron on iodine, it loses 1 electron, only 6 electron remaining on the iodine. Out of 6 electron, 2 electron participate in sigma bond. So it is 2 sigma bond and obviously 2 lone pair of electron. 2 sigma bond and 2 lone pair of electron. It is found to be sp3 hybridized. In sp3 hybridized, 2 lone pair and 2 bond pair, and iodine should have positive charge. So this is going to be, band geometry. So same as we have I3 plus, only the difference is instead of surrounding chlorine atom, we have to have, let's say, iodine atom there. Same if we have ICl2 minus, or if we have, let's say, I3 minus, out of 7 electron, it gain 1 more, and if we have 8 electrons, it is, let's say, 2 sigma bond and 3 lone pair. 2 sigma bond and we can have 3 lone pair of electron. Here hybridization state should be sp3d for 5 hybrid orbital requirement. In sp3d geometry, all the lone pair of electrons should occupy, equatorial position. So it is Cl and another Cl atom with negative charge on the iodine. So it is ICl2 minus. This geometry is going to be, let's say, linear in shape. So we have ICl2 plus, we can have I3 plus, ICl2 minus, we can have I3 minus. So one of the geometry is bent, another geometry is found to be linear. So same in the case of, as per I3 plus is concerned, it is iodine, central iodine atom and iodine atom. It should be bent in shape and iodine should have positive charge. It is sp3 hybridized, and same, it may be, let's say, iodine, it may be another iodine atom and another iodine atom. Iodine having, lone pair and lone pair of electron, and iodine should have negative charge here, and in this case this iodine should be sp3 dehybridized. So it is nothing but, I3 minus. So I3 plus is found to be, bent, and I3 minus is found to be, linear geometry. I hope till now we have completed one type of set here related to hybrid state, related to calculation of hybrid state and the geometry about central atom. Same in the case of, anion of oxyacids. So next is, let's say if we have to find out hybridization state of, central atom in hybridization state of central atom in following ions, and also draw their shape or geometry. Here corresponding compound may be sulfate, phosphate, perchlorate, chlorate, chlorite ion, hypochlorite ion. This may be, let's say, sulfite ion. This may be carbonate. And this may be, let's say, nitrate. Now, one of the note related to this is in anions. In anions of all these oxy acids, sulfate is anion of H2SO4, phosphate is anion of H3PO4, perchlorate ion is anion of perchloric acid, and then ClO3 minus is the anion of, let's say, chlorite ion. So in anion of all these oxy acids, negative charge. Negative charge should be present. Negative charge should be present on surrounding oxygen atoms. Negative charge should be present on surrounding oxygen atom. Obviously, with oxygen, in oxy acid, the hydronium ion, H plus ion has to be connected. That's why it is oxy acids initially. And after losing H plus from oxygen, oxygen should acquire negative charge. So here again, one by one, you can see, let's say first one is if we have, let's say, sulfate ion. In the case of sulfate ion, sulfur valence shell consists 6 electrons, and out of 6 electron, as 4 surrounding oxygens are there, it can form 4 sigma bond with 4 surrounding oxygen. Now 2 electrons remaining here. So 2 electron means maximum it can form 2 pi bond also. So as per hybrid state of the sulfur is concerned, it is found to be sp3 hybridized, and in this case sulfur will form tetrahedral geometry. Sulfur will form tetrahedral geometry here. So it is SO2, it is SO2, and sulfur oxygen should consist one negative charge here. Since out of 4 oxygen atom, valency of 2 oxygen atom is already satisfied. So here we have, let's say, sulfate ion, and this geometry is known as tetrahedral geometry. This geometry is known as, let's say, tetrahedral geometry. Apart from sulfate, next is, let's say, phosphate. So PO4 3 minus in the case of phosphate, which is PO4 3 minus. Here, out of 4 electrons, or out of 5 electron of phosphorus in their valence shell, 4 are utilizing in 4 sigma bond, and maximum it can form 1 pi bond with one of the oxygen atom. And that's why we should have negative charge, 1 negative charge each on every oxygen atom here. 4 sigma bond means it will be sp3 hybridized. And here, if we have double bond O, it is O minus, O minus, and O minus. And this geometry is going to be tetrahedral. You know, this geometry is going to be, let's say, tetrahedral geometry in the structure of, let's say, phosphate ion. Same if you see, let's say, perchlorate. In perchlorate, out of 7 electron in chlorine, 4 are forming sigma bond, 3 are forming pi bond. So all 7 electrons are utilized here due to 4 sigma bond. Its hybrid state is going to be sp3. Its hybrid state is going to be sp3. And in the case of perchlorate ion, again this geometry is found to be tetrahedral geometry. 3 sigma 4 sigma bond and 3 pi bond with negative charge on the oxygen. This geometry is also tetrahedral geometry. Next may be ClO3 minus out of 7 electron. It is forming 3 sigma bond. Maximum it can form 2 pi bond. So out of 7, it is forming 3 sigma bond. Maximum it can form 2 pi bond. And thus out of 7, 1 lone pair of electrons should remaining. As per hybrid state is concerned, it is nothing but number of sigma bond and number of hybrid orbitals. Yeah, number of lone pair. So here total again 4 hybrid orbitals are required and it will be sp3 hybridized. sp3 hybridized, this geometry should be, let's say, chlorine consists of 1 lone pair of electron. It is, let's say, double bond O, it is double bond O and O minus. This geometry is something very similar to that of ammonia geometry. And it is trigonal pyramidal. So if you see more example related to this, apart from ClO3 minus, it is another is ClO2 minus. ClO2 minus means out of 7 electrons, confirmly it is forming 2 sigma bond. Maximum it is forming 1 pi bond, and only 3 electrons are utilized here. And you can say it is 2 lone pair of electron. Its hybrid state will be sp3, and it is chlorine having lone pair of electron, another lone pair of electron. It is a double bond O and O minus, and the shape is going to be, let's say, band shape. So just note down this. I hope you have noted down these structures now. Let's say we can just try to draw 3 more structures related to. It is, sulfite ion. Out of, 6 electrons of sulfite ion, here they are forming, a 3 sigma bond, as we have 3 surrounding oxygen atom. It can form 1 pi bond also. So it is, 3 sigma bond, 1 pi bond, and thus only 1 lone pair of electron remaining there. So 3 sigma bond, 1 lone pair of electron. Its hybrid state should be, sp3. And this geometry is going to be, tetrahedral geometry. Now, this geometry is going to be, tetrahedral, or, it is 1 lone pair. So 1 lone pair means it is lone pair of electron on sulfur. It is double bond O. It is O minus and O minus here. So this geometry is found to be trigonal pyramidal. Trigonal pyramidal geometry. Same in the case of, carbonate ion. Out of 4 electron of carbonate ion, out of 4 electron of carbonate ion, confirmly it is forming 3 sigma bond. It can form 1 pi bond. 3 sigma bond means it is sp2 hybridized. And in this case, as per carbon is concerned, let's say 3 sigma bond, it is oxygen, oxygen, and oxygen, negative charge and negative charge. And the geometry is found to be trigonal planar. And this geometry is found to be, trigonal planar geometry. And same last is in the case of, let's say, nitrate ion. In the case of nitrate ion, out of, 5 electron, here confirmly it is forming, 2 sigma bond, 1 pi bond, or I can say it form 1 coordinate covalent bond. So all 5 electron of nitrogen get utilized here. It is forming sp3 hybridization. And just remember, as per nitrogen plus is concerned, it is same as carbon. So this may be the structure of nitrate ion, and it is, trigonal planar structure, trigonal planar shape. So in the case of SO3 2 minus, it is trigonal pyramidal. In the case of carbonate ion, it is trigonal planar. And in the case of nitrate ion, it is found to be, trigonal planar shape. So in the case of sulfite ion, it is trigonal pyramidal. In the case of carbonate ion, it is found to be trigonal planar. And in the case of nitrate ion, it is found to be again trigonal planar shape. So till now, we have done fair enough example of, hybrid state and their geometries. So it is one of the homework for you. You have to find out hybridization state of, xenon in following compounds, you have to find out hybridization state of xenon in following compound and also draw their geometry. Also draw their, let's say, shape or geometry. So as per these compounds are concerned, let's say it is XeF2, it is XeOF2, it is XeO2F2, it is XeOF4. This may be, let's say, XeO3. This may be XeF4. So you have to find out, let's say, hybridization state of these compounds in following compounds of xenon. I can just try to do 2 to 3 examples for you, and then remaining you can just do practice. So for example, let's say if we have XeF2 xenon, xenon consists 8 electron in its valence shell. Out of 8, confirming 2 utilize in forming 2 sigma bond here, and let's say we have 3 lone pair of electron. 2 sigma bond, 3 lone pair of electron here. 5 hybrid orbitals are required, and thus its hybrid state is found to be sp3d here. In sp3d geometry, in which, let's say, xenon forming 2 sigma bond and then 3 lone pair of electron here. So in XeF2, this geometry should be all 3 lone pair of electrons should go to, equatorial position. It is fluorine and, let's say, another fluorine atom which go to axial position. And thus, as per geometry is concerned, this geometry is found to be, linear geometry. In the case of XeF2, this geometry is found to be, linear. Same in the case of, let's say, XeOF2. Out of 8 electron of xenon, it is forming 3 sigma bond. Here we have 1 pi bond. Out of 8 electron, let's say 3 sigma bond and 1 pi bond. 4 electrons are remaining, and thus 2 lone pair of electron. So 3 sigma bond, 2 lone pair, 5 hybrid orbitals are required again. It is sp3d. Both lone pair should go to equatorial position. So it is, let's say, lone pair and lone pair go to equatorial position. It is double bond O. It is fluorine and fluorine. And this geometry is known as, let's say, T shape. So the remaining examples, including XeO2F2, XeOF4, XeO3, and XeF4, you have to do its practice. I am just giving your final answer as XeO2F2. In the case of XeO2F2, it is also, sp3d. In the case of XeOF4, it is sp3d2. In the case of XeO3, it is found to be sp3. And in the case of, let's say, XeF4, it is going to be sp3d2. So remaining examples, you can just try to practice, and this should be their final answers. Now, apart from hybridization, another important concept in chemical bonding is, bond parameters. Bond parameters, and in bond parameters, let's say we have, bond length, we have bond strength, we can have, let's say, bond angles here. So as per bond parameter is concerned, for example, if we have any bond of, let's say, suppose, for example, if we have H2 molecule, in the case of H2 molecule, it may be hydrogen, and let's say another hydrogen atom here. So this may be, let's say, one of the H2 molecule, and same as, let's say, another H2 molecule here. Both nucleus is found to be positively charged, and the electron E minus and E minus both having negative charge here. Now the distance between both charges, if it is found to be, let's say, R as a distance between both charge, if R is the distance between both charge, like charge will repel each other and unlike charge will attract each other. So in this case, it is, let's say, force of repulsion this nucleus can attract this electron. So here we have force of attraction, and similarly here, let's say, we can have, force of attraction. So this electron can be pulled by this nucleus, this electron can be pulled by this nucleus, and overall electron and electron will repel each other. Nucleus and nucleus will repel each other. So we have force of repulsion. So, at any given distance between two atoms, there is force of attraction as well as force of repulsion. On this axis, if you take potential energy here, and on this axis, if you take R, let's say, R is the distance between nucleus of these two atoms. Somewhere, it is 0 as a potential energy, it is negative potential energy, and it is positive potential energy. We have both force of attraction as well as repulsion. So you have seen somewhere in the chapter of physics work, power, and energy also. The typical energy diagram of potential energy versus, distance is found to be like this. And obviously it will touch to infinity. So when force of attraction will dominate, potential energy is going to be negative. If force of repulsion will dominate, potential energy is found to be positive. So it is the condition of, stable equilibrium. This is the condition of, stable equilibrium. And this distance is going to be, bond length. This distance is going to be bond length, and similarly, ये जो एनर्जी है, दिस एनर्जी इज bond energy or bond dissociation energy. This energy is nothing but bond energy or bond dissociation energy. So as per bond length is concerned, let's say first we can see bond length. So it is the distance between bonded atoms. It is the distance between bonded atoms at which potential energy of is the distance between bonded atoms at which potential energy of molecule is found to be minimum. Is the distance between two bonded atoms at which potential energy of molecule is found to be minimum. So at a given bond length, the potential energy of, let's say, H2 molecule is found to be minimum. And following factors can affect bond length. Following factors can affect bond length. Just try to copy this and then further we'll move related to bond length. Same, we can define bond energy also. First, we'll see different factors which can affect bond length. So here, first factor is, you can say, extent of overlapping. First factor is extent of overlapping, and in this case, you can say as size. At size of overlapped orbital. As size of overlapped orbital increases. As size of overlapped orbital increases, the extent of overlapping decreases. Extent of overlapping decreases, and thus bond length increases. And thus bond length increases. For example, suppose if we have hydrogen iodide, if we have hydrogen bromide, if we have hydrogen chloride, and if we have hydrogen fluoride. In this case, the overlapping is found to be 1s5p, it is 1s4p, it is 1s3p, and it is 1s2p overlapping. Hi consists poor overlapping, it has bigger sized orbital, let's say 5p, and thus as per bond length is concerned, this should be longer than this, should be longer than this. And if you see their exact values also related to bond length, this bond length is found to be 161 picometer. It is 141 picometer. It is 127 picometer, and it is found to be 92 picometer. I can take one more example here. Suppose if it is F2, it is Cl2, it is Br2, and it is I2. In the case of halogens, this bond is 2p 2p overlapping, it is 3p 3p overlapping, 4p 4p overlapping, and 5p 5p overlapping. In the case of F2, in the case of fluorine F2, this bond is going to be 142 picometer. It is 199 picometer. It is 228 picometer, and it is 267 picometer. So this will be the order of their bond length. So extent of overlapping. As size of overlapped orbital increases, the extent of overlapping decreases, and thus bond length increases. Apart from extent of overlapping, another factor is electronegativity difference. Another factor is going to be, let's say, electronegativity difference. The second factor, electronegativity difference. So here you can say for same extent of overlapping. For same extent of overlapping as electronegativity difference. As electronegativity difference between bonded atoms increases, it acquired more percentage of ionic character, it acquire more percentage of ionic character, and due to oppositely charged force of attraction, bond length will decreases. And here you can say bond length decreases. So for same extent of overlapping, as electronegativity difference between bonded atoms increases, it acquire more percentage of ionic character, bond length decreases. For example, if you see, this is, let's say, CH bond, it is NH bond, it is OH bond, And if it is, let's say, you know, HF bond, you can say so, here, due to maximum electronegativity difference, fluorine acquired high positive charge and hydrogen acquired, you know, high delta positive charge. We have to have force of attraction between these oppositely charged ion. So as per order of bond length is concerned, the order of bond length is concerned, this bond length CH is longer than NH, NH is longer than OH, and OH is obviously longer than, let's say, HF bond. So for same extent of overlapping, as electronegativity difference between bonded atoms increases, it acquire more percentage of ionic character and bond length, let's say, decreases here. If you see their exact values of bond length, in the case of bond length here, this bond length is found to be 109 picometer. This bond length is found to be 101 picometer. Bond length is found to be 96 picometer, and it is found to be, you know, 92 picometer. And as per bond length is concerned. Third is, you know, it is multiple bonds. So as number of bonds between two bonded atoms increases. As number of bonds between two bonded atoms increases, number of bonds between two bonded atom increases, their extent of overlapping as number of bonds between two bonded atoms increases, their extent of overlapping increases, and thus bond length decreases. Bond length decreases. For example, if we have carbon-carbon single bond, if we have carbon-carbon double bond, and if we have carbon-carbon triple bond. So carbon-carbon single bond is found to be longer than carbon-carbon double bond, is found to be longer than carbon-carbon triple bond. Carbon-carbon single bond is, you know, all they have same overlapping, but since it carries single bond, its bond length is 154 picometer. In the case of carbon-carbon double bond, it is found to be, you know, in the range of 134 picometer, 139 picometers. And carbon-carbon triple bond is found to be in the range of 120 picometer. So as number of bonds between bonded atom increases, confirmly, you know, bond length decreases. fourth factor, presence of lone pair of electron. So 4, again same extent. For same extent of overlapping as number of lone pair of electron increases on bonded atoms. For same extent of overlapping as number of lone pair of electron increases on bonded atoms due to their mutual repulsion, bond length increases. Here bond length increases. For example, if we have ethane, hydrazine, it may be, let's say, hydrogen peroxide. Yeah, if we compare between, let's say, ethane and hydrazine only. Or let's say we compare between better is hydrazine and hydrogen peroxide. One having one lone pair, another two lone pair. So, it is hydrazine and, it is hydrogen peroxide. In the case of hydrazine, molecule may be represented as this, and in the case of hydrogen peroxide, molecule is represented as this. So as per bond length is concerned, it should be like this due to lone pair repulsion, and its value is found to be 145 picometer, and this is found to be 148 picometer. So this is just the order of the bond length. Now, as per bond length is concerned, in general, bond energy is inversely proportional to bond length. In general, bond energy is inversely proportional to bond length. So if bond length is found to be longer, bond is found to be shorter and found to be stronger bond. For example, the order of bond energy, if we have HF, it is HCl, it is HBr, and it is HI. So HF is found to be, shortest bond, and found to be stronger bond. So this will be the order. This will be the order of their bond energy. HF bond is found to be stronger bond than that of HCl, found to be stronger bond than HBr, is found to be stronger bond than that of HI. Apart from this bond length and let's say this bond energy, another important concept related to this is it is bond angle. So bond angle depends on following factors. It depends on following factors. Let's say first one is hybrid. Hybridization state. Point is, if we have sp hybridization, bond angle will be 180 degree. If we have sp2, it is 120 degree. If it is sp3, bond angle is 109 degree 28 minutes. If hybrid state is, sp3d, bond angle can be 90 degree, 120 degree and 180 degree. For sp3d2, it may be 90 degree and 180 degree. As per, I'm repeating again, as per hybridization state is concerned, it is one of the factor which decide bond angle around central atom. Second factor is presence of lone pair of electron. So even for same hybridization, for example, if we have CH4, it is NH3, and if we have H2O, carbon, nitrogen as well as oxygen, all three are found to be sp3 hybridized only. In the case of CH4, it is hydrogen here, another hydrogen atom, another hydrogen atom, another hydrogen atom. In the case of, it is NH3, this will be the structure of NH3. And in the case of H2O, this will be the structure of H2O. All three atoms, all three central atoms are found to be same hybrid state as sp3. And we know lone pair bond pair repulsion is more than that of bond pair. So this angle is found to be approximately 109.5 degree. It is found to be approximately 107 degree, and it is found to be approximately 104.5 degree. So you can say due to presence of every lone pair of electron, bond angle decreases nearly by 2.5 degree. अच्छा, ऐसा लिख के हुआ है। Have you note down this? So similarly, let's say third. Third factor is electronegativity of central atom. Electronegativity of central atom. So with same hybridization state, and lone pair of electron, with same hybridization state and lone pair of electron as electronegativity of central atom. As electronegativity of central atom increases with same hybridization state and lone pair of electron, as electronegativity of central atom increases, its bond angle increases. For example, if one is H2O and another is H2S, in the case of H2O, it is oxygen having lone pair of electron, another oxygen having lone pair of electron, it is hydrogen and it is hydrogen here. And in the case of H2S, having lone pair of electron, it is H and H here. Bond pair of electron get more shifted towards oxygen, as oxygen is much more electronegative than hydrogen. Here bond pair of electron also shifted towards sulfur, but not to that extent. We should have more repulsion between bond pair and bond pair in H2O, and thus this angle, this angle become 104.5 degree, and due to less repulsion, this angle is just a 92 degree. So as electronegativity of central atom increases, bond angle increase. Now one more factor. As size of surrounding substituents increases. As the size of surrounding substituents increases due to more mutual repulsion, bond angle increases. bond angle increases. You know, for example, again, if you see H2O and you can see CH3, it is O and CH3, oxygen having lone pair of electron and having lone pair of electron here. In the case of oxygen, having lone pair and lone pair of electron, and it is H and H here, having lone pair of electron and lone pair of electron, and it is let's say it is H and let's say CS3 here. Here size of both hydrogen atom is found to be much smaller, and here size of let's say both hydrogen atom, here you can imagine this may be the size of both methyl group, which is methyl as a substituent here. This may be one of the angle, let's say you can say theta, and here this may be another angle, let's say it is phi. Due to more repulsion between methyl and methyl, so due to more force of repulsion, this theta is found to be less than that of phi. Precisely, it is 109.5 degree and it is close to 110 degree. So till now, in chemical bonding, we have seen hybridization state, sigma bond, pi bond, bond parameter, including bond length, including bond strength and bond angles. So in chemical bonding, still few important topics are remaining, including dipole moment, including molecular orbital theory, including resonance, and van der Waals forces, including London dispersion force, a Debye force, Keesum forces. I hope you note down this. So still in chemical bonding, few more important topics are remaining. We'll cover up these later. So in today's lecture, whatever we have learned, just revise the whole things again. Just do practice from your textbooks, irrespective of your board. So chemical bonding is going to be the key. Chemical bonding is going to be key for your JEE or NEET preparation. So keep revising. I'm going to end my lecture now.